Hello and welcome to this video on working with decibels. We're going to show in this video a couple of tricks that you can use to approximate the conversion between ratios and decibels. And it's once you get used to these tricks, it's really quite a bit faster to do it in your head, and you'll have a sense of intuition about what a dB value means intuitively as far as a ratio without having to run and grab a calculator and kind of feeling lost all the time. Now, the thing to remember with decibels is that by definition, they're always representing a power ratio. So if you're given a voltage ratio, then to convert to dB, you have to square that ratio because the power is proportional to voltage squared. So there's just no such thing as a dB ratio that's not referring to power. And that keeps things straight if you're mixing, doing some system calculations, and maybe some parameters are coming in as a voltage and some are coming in as power. dB is always going to be representing a power ratio. And the formulas to convert are set up appropriately to keep it that way. Now, another aspect of the definition is that it's just based on a convention of taking the exponent of a power of 10 and multiplying it by 10. So simply, if you have 10 to the fourth, a ratio of 10 to the fourth to 1, you just take that exponent of 4 and multiply it by 10, and you get 40 dB. Or if it's 1,000, 10 to the third, you get 30 dB. So that's really quite simple. Another thing that is appealing about the dB scale, dB system, is that since you're working with exponents, the process of operation of multiplication when you're cascading blocks becomes addition. And division likewise just becomes subtraction. So this is great. It's all quite simple so far. You just take these exponents and multiply them by 10, and you've got your dB. So that aspect of this whole thing is quite simple. Let me just put a square around that. And then this aspect, of course, we find appealing overall. The problem is that we are more interested in working with all numbers, not just powers of 10. So that's where things get a little bit messed up, so to speak, not as intuitive. So the question becomes, how do we deal with all those values in between 1 and 10? And in reality, it's actually possible to, by memorizing just a couple of values, we can get really far. So let me draw a little table here, and we'll see how this works. So let me write down the ratio values. And we'll figure out what the dB equivalents are. So let's start with 10. And we'll work our way down to 1. Can kind of just barely fit it fit it in there. Now 10 is 10 to the first power, and times 10 just equals 10. So that's pretty easy. And 1 is 10 to the 0th power, and that times 10 is 0. So we got two values right there. Now the next one is one that you just need to memorize. And 2 is actually 10 to the 0.3 raised to the 0.3 power, approximately. These are all totally approximations, kind of just to get you by. But like I said, 2 is approximately 10 raised to the 0.3 power. And multiply that by 10 and you get 3. So if you memorize that a ratio of 2 is 3 dB, you can actually get pretty far, because now we already know that 4 is 2 times 2. And in the dB system, multiplication becomes addition, and we just saw that 2 is 3, so 4 is 3 plus 3, or 6 dB. And similarly, we get 8, because 8 is 2 times 2 times 2, and that's 3 plus 3 plus 3, or 9 dB. Also, if we get clever, 5 is 10 divided by 2. And 10 is 10 dB, and divided is a minus, and 2 is 3 dB. So 10 minus 3 is 7 dB. Now, another value that you might want to memorize is a ratio of 3. And that works out to a very coarse approximation to be 5 dB. And we get there from taking 2 to the 5th, which is 32. So 2 times 2 times 2 times 2 times 2 is 32. And if you divide by 10, you get 3.2. So that's instead of 3. But let me just write this out here. I'll make a little bit more room to do that. Okay, so for this value of 3, what I'm saying is 3 can be thought of as 2. Switch back to a pen. Two times itself 5 times, and then divide by 10. So what you end up with is, converting to dB, 3 plus 3 5 times minus 10 works out to 15 minus 10, or 5 dB. When you add up all those 3's, you get 15, and then subtract 10 and you get 5. And it's a very handy value to work out the rest of the numbers. So let me just highlight these numbers that are kind of the basis or easy to remember. And I'll go ahead and highlight the 3. It's kind of good to memorize that 3 is about 5 dB. That one is a really loose approximation, so you got to keep that in mind when we work with some of these other numbers. But now that we have 3 in the picture, we can say 2 times 3 is 6. And so that becomes 3 plus 5, or 8 dB for the value of 6. Now from here, you could just say, okay, so what's 9 as a ratio in dB? Well, it's between 8 and 10 on the ratio side, and we could just visually say, oh, that's about, these are halfway in between. 7 is 8.5 and 9 translates to 9.5. If you're of an engineering mind and you want a little bit more rigorous approximation, we can do a trick this way. Looking at 7, you can think of 7 as being the square root of 49, and written with a different notation, that's 49 raised to the 1/2 power. Well, 49 is pretty close to 50, so we could say 7 is about the same as 50 to the 1/2 power. And 50 in dB is 100 divided by 2. So that's 100 is 10 squared, or 20 dB, minus 3. So 50 is 17 dB. Now, that would be for the 50, but to take into account the raised to the 1/2 power, once you're in the exponential world, that means we take 17 and multiply it by 1/2, working with exponents in a logarithmic scale. So 17 divided by 2 is roughly our dB equivalent of 7. And that indeed gives us the 8.5. So it's a little bit more, it's kind of an oxymoron, a rigorous approximation. And you can do the same thing with 9. 9 is really, can be thought of as the square root of 81, which is pretty close to 80. So maybe I'll leave that as an exercise. See if you come up with 9.5. Getting yourself to the dB value of 80 and then dividing that by 2. Because this is 9 is roughly equal to 80 to the raised to the 1/2 power. Okay, so now we have equivalents for all the numbers between, all the integers anyway, between 1 and 10. Okay, so let's look at some examples working with this table and the exponents to convert ratios to dB. And let me just make a little bit of room and move things, slide things over just a little bit. Okay, so let's look at some examples of converting ratios to dB. Let's take 100, for example. So 100, we can just say is 10 squared, and here's a case where you just multiply the exponent by 10, and you get 20 dB. Well, what about 200? Well, that's just 100 times 2. So we had 20 for the 100, and times becomes plus, and 2 is a factor of 3 dB. So we get 23 dB for a ratio of 200 to 1. If we go the other direction and take 50, that's 100 divided by 2, or 20 minus 3 gives us 17 dB. All right, let's look at a different kind of number, 6,000, for example. So that's 1,000 times 6, which would be, 1,000 is 10 to the third, so that's 30 multiply that by 10, you get 30. 30 dB plus 6 is a factor of 8 dB. 30 plus 8, so we get 38 dB. Similarly, 5,000, you can look at that as 1,000 times 5, which gets you 30 for the 1,000, and 7, factor of 7 for the 5, or 37 dB. Or you can think of it as 10,000 divided by 2. So 10,000 is 40, and minus for the division, and 3 for the 2 also gets you there, just 37 dB. Now what about fractions? Let's try looking at, for example, 1/2. Well, 1 divided by 2. 1 in dB is 0. Division is subtraction, and 2 is 3. So we get 1/2 is minus 3 dB. Similarly, for 1/4, we get 0 for the 1, a minus for the division, and 4 is 6 from our table. So we get minus 6 dB. Let me clean that up a little bit. So negative values in dB refer to fractions, fractional ratios. So the concept of a negative number is used differently in the dB system. It's pretty much just for fractions. Let's look at a couple more fractions. Let's try 100th. That just gives us 0 minus 20, minus 20 dB. And now what if we have a different value in the numerator? We can do it, work the same way, work right through the division and get, 6 minus 20 in this case gives us minus 14 dB. Now, for 100ths, you might be presented as 1/25th instead. So if you were to work with 1/25th, what you have to do is convert 25 to dB, and 25 is, you can think of that as 100 divided by 4, which in dB becomes 20 minus 6, or 14, gets you right back to the same place. So 1 over 25 is the same as 0 minus 14 in the dB system, gets you right back to the minus 14 when you put it in the denominator, so to speak. So that gives you an idea of how to quickly convert to dB if you just practice a bit with those manipulations, primarily trying to factor it into powers of 2, and then occasionally a factor of 3 can get you pretty far converting from ratios to dB. Often, the more perplexing question is, or pressing question is, going the other direction. That is converting from dB back to a ratio. And so let's see how we can do that quickly in our head as well. Okay, so in the end, it's really pretty straightforward to convert from dB, and it's almost embarrassing not to be able to explain it, because if you overthink it, you can make it a little bit more complicated for yourself. But let's say we have an example of 63 dB, and we want to convert that to a ratio. Really, with your dB values, what you just need to do is kind of draw a line ahead of the first digit and break it apart that way. So now if you draw a line such as what I've done here, what you end up with is the order of magnitude and then on the left, and then the quantity on the right. So in this case, we have 10 to the 6th, so millions. And then the quantity is 3 dB worth of them. So what we need to do is build ourselves a table of approximations going the other direction from dB back to ratio, back to the ratio world. And we can do sort of the same table that we did before, but this time with dBs listed out. On the left. And we'll convert over to ratios. So 10 dB we know is 10 to 1 in ratios. And 1 dB, well, that's not so simple, right? We know that 3 dB goes straight over to a ratio of 2 to 1, because we memorized that. And similarly with 5 dB, we have to sort of remember that that goes to 3. And now some of the easier numbers are we have to work with addition on the left and translate that way. So 9 can be thought of as 3 plus 3 plus 3, and converting to ratios, that's 2 times 2 times 2, or 8. So we have to express the dBs as sums of the numbers that we know, 3, 5, pretty much 3 and 5 all the way, and possibly 10. So 8 is 3 plus 5, and that works out to 2 times 3 when we translate to ratios, or 6. Six is just 3 plus 3, which is 2 times 2 in the ratio world. Now for 7, we can look at that as 10 minus 3. So that's same as saying 10 divided by 2, or 5. Now some of these numbers that look a little bit more obvious are actually less obvious, going from dB back to ratios. So 4, which was easy converting from a ratio to dB, let's think of 4 as 4, you can think of as 10 minus 6, which is the same as saying 10 divided by 4 in the ratio world, gives you 2.5 for a ratio. So dB of 4, dB value of 4 is a ratio of 2.5. And then 2, we can think of as the difference between 5 minus 3. And in ratios, that becomes 3 halves, or 1.5. And for 1, we can take the difference of 7 minus 6, and converting that gives us 5/4, or 1.25. So a little bit different distribution of values going from dB, building that table, to go from dB to ratio. But now that we have that table, we can look back at our original problem. We have millions and 3 dB worth of them. That gives us a quantity of 2 in an order of magnitude of millions, or 2 million. To convert that number. All right, let's try another example. Let's try 27. And I'll just draw a little line. Between the magnitude and the quantity values here. So we have magnitude of 100s, and the quantity is 7. If we go back to our table, 7 gives us a ratio of 5. So 5 hundreds, or 500. Now let's take a quick look at negative dB values, because those can kind of trip people up. But they work out to be pretty simple if you're consistent. Let's try minus 27. And the trick to employ here is just to remember that minus 27 is really nothing more than 0 minus 27, right? So we figured out that 27 is 500. So if we convert that back to a ratio, we need to go from 0 gives us 1, and the minus sign is division, and we already figured out that 27 is 500. So minus 27 is 1/500th. Now, you may not want to work in fractions and would prefer to go straight to decimals instead. And that's actually pretty easy in dB, just using a little trick. Let me write this minus 27 again. And now our objective is to get a decimal instead of a fraction of 1/500th. So the trick we do, I'll change colors back to show the trick. We want to make the original value positive. And just like when you're working with fractions, you can multiply the numerator and denominator by the same factor, and you don't change the ending value. With this dB expression, we can really add a power of 10 to make it positive, and as long as we subtract it, we'll end up with the same value. So in this case, to get the nearest power of 10 to get it positive would be 30, or not power of 10, but multiple of 10. So if I add 30 and subtract 30, I still have the same value, but I've just kind of refactored it. So now what I need to do is perform the arithmetic on the front part and then convert it. So 30 minus 27 gives us 3. So that gives us 30 minus 27. So that's the same as 3 minus 30. And now if I convert, 3 becomes 2, and minus becomes division, and 30 is 1,000. So 2 1,000ths is what I end up with in a decimal representation. And it jives. So those are some quick approximations you can do to go back and forth between dB and ratios. And if you just practice with it a little bit, you will get quite quick with it and build an intuition of what dB values represent in real world numbers without having to run for a calculator. It's kind of a very sort of a blind feeling when you have to run to a calculator to get any sense of what the dB value is. And if you can do a quick approximation, it's as if you start to kind of speak the language instead of blindly translating each figure individually. And you get a real handle on magnitude and so forth. I think a common joke is by the time you reach the calculator and figure out a value, the meantime the equipment on the bench is smoking and you've ruined a sensitive power detector, for example. So hopefully you can avoid that with a little bit of practice working with these little tricks. All right, hope it was helpful.